Yeah, good morning, everyone. I think we can start now.
Good morning, sir.
Okay. Yeah, thank you. So, this is regarding a two-day workshop on VLSI design, and this is from the ChipXpert. We are conducting this two-day workshop from the all the way how the chip design will happen from specifications like the requirement for any of the industry to the all the way how it will get manufactured. Okay, so to understand in detail, right, we'll start with today with from the basic level. Okay. So what is VLSI and what side the VLSI is in the industry and how the industry of semiconductor is booming, and some people may confuse like what is semiconductor, what is VLSI, embedded or core field. All these things we can clear it today. I'll give understanding in the first 5 minutes what actually the VLSI where it is coming. Okay. And I'll take the doubts in the last. Please note it in your note. We will take a 15 to 20 minutes of the doubt session also today and tomorrow. So you can ask any of the things, basic or advanced or anything that is related to your career. At the same time, even you are working in industry and even you are a basic student from second year or third year or a fourth year. I see some of the colleges are also joined for this workshop. They're projecting this, and also at the same time, the students are from the multiple colleges from India also joined today. And at the same time, I just wanted to give a complete understanding of the VLSI. Okay. So before starting on this today's session, so just think like where is VLSI? Yes? Can you mute someone? Yeah. So today's session we will start with what actually the chip design flow. Okay. So first thing is like this main focus of this VLSI will be was coming from last 3 4 years, but before that where we are on. So to understand that, right? So this VLSIS comes under the electronics field. Okay. In the electronics, we see that the completion of bachelor's or in the time of bachelor's, the people who are background in the electronics, let's say triple E or EC people, or a people from the instrumentation, electronics and instrumentation engineering can do this course, or they can enter into the core field. And in that, we have like multiple core jobs. Multiple core jobs include like embedded systems, communication sector, and electronic sector and semiconductor sector. Okay. In the electronics, there are multiple things. Out of that, we have, uh, we have, can someone mute? I think there's a disturbance and yeah. So in the sector of core field, in the ECE, we have multiple sectors. In that, the electronic sector, we have one more is semiconductor sector. What is semiconductors? Basically, we have the conductors, semiconductors, and the insulators. As you know, right, the conductor will conduct directly the flow of electrons, and the insulators are it will block completely flow of electrons, and semiconductors are the where it will react to the particular voltages when you give a flow of the flow of current or a voltage to it. Okay, so it will act according to the threshold voltage you have given. So now coming to the field of the semiconductors, when you give a small voltage, let's say a small LED, comes under the semiconductors field. It's a small semiconductor, right? It's a diode. Okay. So the evolution of chip was started with the semiconductors. Okay. So we see that in the VLSI, the VLSI is a field, is a part of the semiconductors where the chip designing and manufacturing will happen. Right? So there is a two things to understand first. What is that? First is the design and the manufacturing. Design is the designing of the complete chip. It's not like we are manufacturing. Let's say you have a picture to make a design and you print it on a printer. That is called manufacturing. And the same thing when it comes to the chip designing also. So I'm talking all about today is about the VLSI design. So how we design the chip, the small chip which will have a billions of transistors in it. So how are we going to design it? So we're going to learn this. Okay. Now let's see where these chips are getting used now. You see that everywhere in this world now, completely electronics that has smartphones, laptops or EVs, I mean the electronic vehicles or smartwatches, medical devices, wherever you see, all these are having the chips. You see the mobile processors, laptops and smart devices, IoT devices, sensings or cameras or like any sensor. You see a small fingerprint sensor, a small camera or a small detection like sensing things. All these are in the medical field will be comes under a chip. They use the chips actually, the ICs, what is integrated circuits. Okay, so we are developing that chips and manufacturing was done by the foundries, manufacturing units. So that is something different that when the design is done, the equivalent manufacturing team will do that manufacturing process. Okay. So let's understand the VLSI design flow first. Okay. I'll also go with the manufacturing process. Okay. But to understand how the design flow will work first. Okay, in the design flow, right, we will be learning today about what is the requirement for the VLSI basics, okay, and VLSI design flow, and what is front-end design and what are back-end design, what we will call, and how the manufacturing, that fabrication and the packing of chip will done, and how the careers in the VLSI. And before starting on this, I just wanted to give the background of this workshop first. So I'll cover in the first 1 hour about the VLSI design flow, okay. The next 1 hour, okay. The next 1 hour, I'll be taking on the how the chip we design from the from the start of the specifications requirement to the all the design flow. At the same time, we'll use the how the tools are used in the industry to design the chip. We'll take a small chip.
Hello, sir.
Sorry, your voice is not audible, sir.
Audible, sir.
Just give me a
Not
minute.
audible.
Oh, is it just it is the voice is not audible, or should I take it 1 minute back?
Now it is
Can you
audible,
mute
sir.
all?
Now it is audible, sir.
Okay, someone has unmuted me,
Yes,
muted
sir.
me probably. Yeah, please don't unmute me. You're gonna miss the hours of time, like because we have only 2 hours. Okay, please don't unmute me. Okay, yeah. So to understand, so where I am, so where you missed from?
From the
Sir,
basics.
when you shared this image, at that time your voice was not audible. The slide is not showing here.
Is it now?
Yes, sir.
Yes, sir.
Yeah, sure. Thank you. Okay, so Here, right, is it the one? Okay, so basically the transistor is an electronic switch. So I will repeating again, the transistor is the electronic switch where it will act as a switch or on and off when there is a sub-threshold voltage is applied for it. Let's say a one voltage transistor will on or off at a 0.3 or a 0.5 voltage. So that is like electronic switch where a threshold voltage is applied for a transistor. Okay. So now I just wanted to bring up your fundamentals back. How the chip will be designed. Okay, this is mainly important to understand for your future things. Here, they first design the diode, which is like a PN diode, or a normal diode they have created. On top of that, they have created one of the PNP diode, NPN diode. Of that, they have created some MOSFET. It's an evolution of the transistor I'm saying about now. After the MOSFET is created, they think that this is something acting like weird when the voltage is applied, it is acting like something different. Some threshold of voltage. Then they have combined the different MOSFETs to form NMOS and a PMOS. They combine the both of them to make a CMOS transistor, which is acting as a NOT gate. So functionality of the NOT gate is like when you give an input of 0, it will act as a opposite to the what you have given. The output will be the 1. Let's say you wanted to on the switch, it will off the switch. It will act as a opposite what you wanted to do. So that is called as a NOT gate. Out of that NOT gate, the transistor they have created, the NOT gate or a NOT transistor, what it can say. They have combined the NOT gate to form OR gate or AND gates. I think you might have.
So you're unmuted.
Please don't
Sir,
unmute me.
no,
Someone is getting unmute me. Okay? Please don't do that. Okay? Yeah, or else I have to make that, I have to unmute everyone and no one will get a doubts to ask first. That's the reason. Okay? Yeah. So just to understand the logic gates, they have created a number of NOT gates with a number of different logic gates with using the NOT gate. And they have created on top of the using this logic gates. Let's say these logic gates are the basic implementation of the transistors. Let's say to understand basically, you have alphabets and you have created words for it, right? Created words. Then you have created a stories, you have created a objects, you have created a all these things representation was done. The same way this how the evolution of the transistors was made to the logic gate, that is the representation purpose. Then the logic gates are like adders on top of it. Using the logic gates, they have created adders and muxes, all these things. On top of that, they have created a muxes to store the logic. Let's say you wanted to store some data, it's required some logic. With that, they have created sequential logic, which will be having the clock as an input. When the clock is on, the logic get enabled to store the data or read it and read the data or write the data. With that, they have created a memories or a intelligence that chip has to do. That is called as a ALUs, arithmetic logical units. They will perform the instructions. Let's say you wanted to process something. Okay. And they have created a memory interfaces or a buses or inputs and outputs for sensors or that is they have created. With that, we can combinedly create a full processor. Let's say I wanted to design a chip that is like an adder, which will add the like a calculator. For that, there is a chip needed, right, to addition, subtraction, multiplication, all these things. So that's all will be created with the transistors, which using this basic logic gates which we design. Again, that will be converted into CMOS transistors. That is, CMOS transistors will have a physically they have a different metal layers that are called as a P substrate or N substrates or insulators. All these things combined they form a transistors. Now you can assume a 1 billion transistors required in your mobile to run your all your operations. Now you assume how many logic gates are required, how much the design things are required. Okay, if you see the evolution of the transistor, right? From 1947, if you see the number of transistors, it's been like they have invented the transistors in the labs. It's been like we have a billions of transistors currently. The evolution was like it was started with CMOS, but now we are at FinFET technology and GAFET technology, which is gate all around, which will be using the okay. So that is like evolution is like we call it as a small scale integration. They're used to call it as. Now we are at having a billions of transistors in a 1 centimeter size of the chip will having a at least 10 billion transistors. The modern mobile will have at least 3 billion transistors. Okay, that evolution we call it as a technology. 3 nm, 4 nm, or 2 nm. Okay, so let me understand deeply about that also. So if you see the graph of the things, in 1947, we used to have only 2000 transistors in the size of 2-inch processor. Now, if you see, we are at 2 billion transistors by the 2011. I didn't have a graph till today, but we have more than 20 billion transistors in a size of 1 centimeter. That is the one we see. Okay. Next thing, so as coming to the VLSI design flow now. So as we covered about the VLSI basics, what is the fundamental things? Now we'll start with the how the design flow will start for it. Okay. So first, for any of the application, we need a requirement. Let's say you need to have a chip to for any of the functionality because that is the memory or element that will perform the actions. So is it my voice is clear or is need to correct something?
Excuse me, sir.
Yes, sir, it's good.
One suggestion from my
Thank you,
side,
thank you.
like,
Just someone is raising the concern. That's us. Okay, thank you for that. Yeah. So to as we start on the design flow overview, right? So first, right, for any of the applications, let's say you need a let's say you wanted to design a elevator which will perform 100 floors. For that you need a new chip to design because a normal chip will not work at a speed that it has to operate or a sensors to operate for each and every floor because some functionality fault is happened at 13th floor. It has to cross check. Okay, let's leave it about the lifting. Let's design a Tesla processor now. How many sensors are required for it, let's say, and how much speed it has to work it at. And if something happened for a 0.001 second, some glitches happen, what will happen for that car or a person sitting in that? Because it is automated car, right? You think the chip inside, even the car was built in 2016, but chip was not built till the 2020. It took 8 years. Even the car was started to plan in 2013. The car was built by 2015 itself. At 16, the final prototype was came to the market, but chip was multiple failures happened because of some sensor failure, and the chip was having some 0.1 glitch that can make it fatal to the person also, right? So that much efficient the chip has to work. For that, we require the proper specifications that chip has to work. The speed, it has to work at 10 gigahertz. It has number of cores, a number of sensor supports, input and output. The chip has not to get heat. It will the heat the chip gets heated or it gets more heated, then the functionality also failure. Exactly. That's good thing. So how the things will someone having an echo for me. So that's how the things will be we have to consider for the specifications. With the specification, the basic RTL code will be designed first. Okay, so RTL code is like a just like number of how much the memory is required, number of cores are required, and all these things are defined at the RTL stage. After that, they will design the each and every behavioral code. The behavioral code is like just a 1 GB data required for this. That 1 GB data or 1 GB memory thing will be implemented with a proper hardware description language that can be VHDL, Verilog, or system Verilog code. And it is properly verified by the functional verification team, that is the design and verification team. And let's say your design has a 1 billion gates or 1 billion logic gates, let's say. It required the double the size what they have planned. It costed a crores of money if the size of the chip is increased by 0.1 micrometers also. So that what they do, they will synthesize the logic. Let's say synthesizing the logic is like to design the full header. How many gates are required? Anyone answer?
5 gates.
Your voice is not clear.
Excuse
Okay.
me, sir. One suggestion from my side. Let us mute everyone, and after completion of the session, you can provide some time for the doubt session, sir.
That's
Keep
yeah,
on your
that's what I
voice
said.
is
That's what I
breaking
said.
due to
The last 15 is for the 15 minutes for the dot session. Okay.
Yes, sir.
Okay.
Yes, sir.
Yeah, don't ask the doubts in the middle because people are actually interested in listening, so they may miss the flow of the things. Okay. So don't ask any
And one
doubts.
more
Now, please
thing,
note the
sir.
doubts in your notes. I'll take each and every questions today. Okay.
And one more thing, sir. The admin who taking care of this setting can mute all. There is no option for unmuting the mic. So then
Yes,
it
yes,
is
thank you.
easy
That
for
they can
you
do.
to
Please,
continue.
Santosh or Rahul, just take the things, no? I think if you join, yeah, sure. Thank you, man. Yeah, thank you so much. Okay, so where we are. So the synthesize is a part where you're synthesizing the logic. A person can design a full adder with 10 gates, but is it required 10 gates to design with all the AND gates and all gates? No, right? It's a simple 3 gates or 2 gates are enough to design the logic. That is called a synthesis. You're optimizing the logic. How you optimize? The simple techniques in our digital electronics we see is like a K-map. How you synthesizing the logic, right? So with that synthesizing, you will be having an optimized logic in the format of Verilog code. So Verilog is something, it is like a hardware description language. The logic, whatever the circuit, whatever should the AND gates and OR gate, that will be represented in the form of text format. The text format is called as the Verilog file, where the hardware, the circuit which you have will be defined it in a text format to readability, so synthesizability for also for analyzing the data for simple way. Let's say you have a 1 billion gates. It's hard to see within a circuit, but it is easy to analyze in a text. Okay. Yeah. Okay. So that's how the things will happen. And the next, the physical design is the way. So physical design is the way stage you will be physically implementing this logical data on the silicon. Okay, how the physically they implement that each and every gate is a combination of transistors. Let's say AND gate is a combination of 4 transistors. That 4 transistors will be physically implemented. The CMOS design you see, the CMOS layout, what you see, will be really implemented on the silicon. That's how the chip will start functioning. Not like just a AND gate and AND gate what the logic will be, just you will go and print it on the board. Will that work? No, right? So it has to be physically printed on the board. That will be done by the manufacturing team. The next, after it is implementing each and every gate on the board, there is all this process will take. From the design specification to the physical design, it will take at least 2 to 3 years of time. Okay, now the manufacturing process that is called a fabrication and packing. Fabrication is a process where you will be fabricating the chip the cycle of 6 months. That 6 months, after that, it will take at least 3 to 4 months to properly validate and pack the chip. The packing is like a process where the small 0.2 nm, 1 nm widths of that pins will be properly has to connect it to the motherboard. It has to have a proper analog connections, analog routing to be happen to connect to the motherboard. After that, it will be properly tested, and out of every 100 chips, only 50 to 60 chips will work. And that 50 to 60 chip will go to production, that is in your mobiles, and it will just take you 15 days to install your mobile. But the process of chip designing, it will take at least 3 to 4 years for a small scale processor. Okay. So let's cover each and every topic in detail now. Okay. So specifications, let's say the specifications, like whatever it may be, like you are using it in a laptop or a car, whatever it may be, it requires the chip. It will be created on the parameters of the how much the chip speed it has to work it out. You see the 2 gigahertz the chip is working. Can someone say what 2 gigahertz it means? It means that, but it means that it is the clock period basically, right? The clock period is the inversely proportional to the speed. How it is inversely proportional to the speed? Your 3 gigahertz is equals to the, or let's say 1 gigahertz is equals to the 10 to the power of minus 9 seconds. Means the chip has to work it out at a speed of 0.1000000000001. The instruction for each of the thing that will happen at that speed in the chip. What is the instruction? Instruction is like adding any of the things, 1 plus 1, 2. That is the instruction for a chip. So that has to work at that speed. And that instructions will happen at that speed so that all the parameters will work at that speed. And the power, what is the power? It has to use the very low power so that it will give a more battery life or a less power consumption for your application. If it is using a lot of power, then if you're handling a more and more appliances, then it will cost you more power consumption also. And the area of the chip also matters because silicon is too costly. The material of silicon is more than the cost of a gold, if I can say. And there has to use some, yeah. Okay. Next, so first coming to the VLSI design flow, the idea and the specification will be there, and the design architecture will be designed by the architecture team. What are the requirements for the chip? They'll accordingly design. Then the RTL code will be designed. Let's say RTL code, it has a very basic code of the hardware description language. Like let's say it need an adder to use. It will use the adder directly, but it will not have the real gates in that. When it is designed by the design engineers, design and verification people, they will be creating the each and every gate and validating the glitch and any of the corner case issues, they will be addressed and functionally properly verified whether it is working as per the functionality of the requirement or not. Let's say I wanted to design a calculator circuit, right? It's a basic question when we ask for any of the interviews also. I wanted to design a calculator that will perform at least a 3-bit of data. 3-bit is like 9999. For that, if someone is pressing minus, it has to do the minus calculation. Someone is pressing plus, it has to perform the plus application. So to design that, even it is a minus or a plus, let's say a number called 999, a number called 999. Just a second.
Someone else is sharing the screen.
Yeah,
Sir.
someone is
Sorry,
sharing
sir.
this.
Sorry to interrupt you, sir.
Yep.
Hello.
Someone is taken my screen sharing. Let me reshare. Please don't take the control of my PC. It is going to waste your time because it's important. We have a lot of things today. Okay. Please don't do any sharing of screen or unmuting yourself because a lot of people are joined. We should not disturb their attention. Okay. Sorry for that. Just I'll take the control back. Yeah. Okay. So here the functionally the RTL code is converted. That is a register transfer level that is converted into real design code. That is hardware language that will be validated by the design and verification people. Along with that, the logic synthesis team will synthesize the logic. To say 1 billion gate count is there, they will be making it to the off of the port so that the area of the chip will be lesser and the power consumption is also consumed lesser by the each and every gate. Let's say each and every gate is consuming 0.001 millivolt of current, and into one, at least we say 1 billion transistor, then it will at least consume 1 voltage of power per hour. Then it will give at least 3000 minutes of power to your mobile. So that's how the power will be calculated. Since simplify, I'm saying, but there are specific calculations that they will do in the physical design process where they will be integrating in a physically. How they implement physically is like, let's say you have a particular RAM that will be having a 2 GB RAM. So they'll be having a IP team. They will design these RAMs by the same process of this. They'll be in RTL code. They'll be go to all the process that will act as a RAM. How much the bit speed it is required. Accordingly, they will design on the processor all this with the tools. Again, the process will be printed on the silicon die. The die will be having a number of chips will be printed like this. It will take at least a 6 months process to go to the all the 400 cycles. And if you wanted to understand how this miracle of things will happen, you can go and watch some fabrication process of the chip design. That's how it is more than a medical things. That's how we're dealing with it currently. Let's say our nerves in our body have at least 0.1 microscope. We can watch our nerves, how they are behaving. But if you see our circuits at nanoscale, that is 10 to the power of -9. We are designing a transistor set that small now. Current technology, the size of transistor is at 1 nanometer. It means that the P2 NMOS, the channel length is 1 nanometer. I mean, the size of transistor will be at the double the size of the channel length, probably. That scale we are designing the transistors. Okay. Let's cover each and everything related to the RTL code and specifications. The specifications include how the performance has the chip has to manufacture, that are designed. At the same time, the physical dimensions, the size of the chip matters, and the design technique for user for this. The ASIC or FPGA or SoC, these are the design techniques. Someone says ASIC is application specific integrated circuits. Is like you can use for only for certain applications. Let's say you wanted to design a chip for a car that can be used for only for that car sector. FPGA, you can still feel that is like a programmable chip. You can use some hardware languages to redesign chip to work for particular application. How? Like let's say a lift will work at 10 floors. The same lift will work for at 5 floors also. You can still use as a chip for different functionalities. SoCs that are called as a mobile processors or a laptop processor, a system processor, or a TV processor are called SoCs because system on chip where all the different type of memory elements, RAMs, or Bluetooth, or the network chip, or like all integrated in a single circuit. That is called a SoC. And technology that is used, that is called how smaller the technology, the more the number of transistors will be there. Okay. To understand that the recent India has a chip manufactured in India at what technology, if you know, at what technology the India has manufactured. India has manufactured at 180 nanometer, which is like a technology in the 2001 or 1999. And there is a manufacturing unit that was started in the Gujarat, which is a scale of 5 nanometer that will be functional from in the 2028. Okay, but still the market we are at is 2nm that is manufactured by the TSMC and the Intel. Okay, so this is how the technologies matters. And next, the synthesis, RTL synthesis. The RTL synthesis, right? Here the logic, the RTL design and synthesis. Yes, please. Someone mute, please. Okay. So here, right, in the RTL, right, we will be defining the logic, but it is not completely the logic circuit will be there. It will be having the basic knowledge, like the basic understanding of the circuit that will be redefined with the all the logical gates like this. All the constraint for each and every gate we have. This is how the complete from the RTL to the design will be making it into the gate level netlist. Okay. Here there is a process where the design people will design complete in a gate level. Again, they will be functionally verified properly whether the requirement is working as per the all the test cases they have given. The test cases like whatever the functionality they have to give, all this working as per their requirement of the chip or not. Then they will be validating with all the RTL bugs they see it in the design will. Okay. As you see the design and verification, the RTL design and verification will comes under complete front-end design. These people will be having the more number of engineers in VLSI design. 70% of the chip development will happen at this step. Okay, the tools used for this are Synopsys VCS and Cadence Xcelium and also QuestaSim from the Mentor Graphics. These are the industry standard tools will be used by the industry. Next, coming to the analog design team. Okay, here, right, someone was asking like why the analog design people will comes under the VLSI. This is like, let's say, let me give you some good story about this for you. Okay, the story is like just don't interrupt me if someone is having any doubts on this, but I'll just have some cover up story for this. So analog people are people who actually design the each and every gate in a CMOS test circuit. So they will be creating each and every logic gate in the format of real layout of the CMOS. How they do? Let me understand. So like, is there any AND gate that will be really implemented in the CMOS and that design will be used by the physical design people? How it is there? Like, let me understand a story about this to understand. You have is, let me understand the way that how the story of a normal movie story, let me understand in that way. You have a story, but you need a character for each and every story. So that characters are designed by the analog people. The story was a design and verification people will be designing that Verilog file or a netlist file, and the characters are called as the, for AND gate there's a character. That characters will be designed by the analog layout design people. Each and every gate that or memory element or PLL or digital to analog converters, op amps, everything will be designed by the analog layout. These comes under the backend people designing it in a graphical way. The tools used for there are Cadence Virtuoso from the Cadence. And the caliber is to verify all the functionality things and also layout errors in the design. Okay, now what the physical design people will do, the question will be. So they actually direct this complete chip, how they direct, where to place, how the power has to come, how to act, and any glitches in the timing. All these things will be designed by the, physically by the their area. The process includes they are converting the physical design involves all the gate level Verilog netlist into layout format by combining this analog layout and the logic. Combining the design of that Verilog file and combining this analog circuit together, they'll create a actual netlist which will have the technology mapping will happen. The technology mapping is like that each and every CMOS they have created will be combined with the logic in your Verilog file. Combined, they will create a physical design on a real silicon. So this is how they design the real chip. So each and everything that is having a planning for it. The planning includes floor planning, power planning. Floor planning is way to place each and everything in the design. That is floor planning. Power planning is like each and every gate, the 1 billion transistors, each and every gate they should have a, someone has to cover my, again, the screen sharing. Okay. Yeah. So it includes the floor planning and the power planning and placement. Okay. And clock tree analysis and routing. All these are the process where it will include the physical design flow. All this gate level will be converted into real-time layout where the chip actually how it's going to print or how it is going to fabricate the actual bodies. Okay. It has to meet all the frequency, that is the speed of the chip and the power requirement. It has to work at this much power only. Okay, and functionally it has to work at that perfectly. Okay, so this is how the physical design process. Now, to understand the fabrication process, it will be printed on the complete silicon wafers. The wafers are like a slice of sheet, which is silicon, where the chip is completely manufactured on that. And it is involves the photolithography process, doping, etching, and decomposition of the different layers. Completely, someone is again taken away.
Sir,
Okay.
screen share.
Please don't do that actually. Yeah, it's wasting the time actually. Yeah. Because next step you have the analog things. I mean the digital design of from the specifications to the all the RTL design. Okay. And the next thing includes the packing and testing. This will includes completely how the chip is going to place on the motherboard for the pins to connect. Okay. Please don't do that. Someone is doing again and again. Just give a second.
Hello, sir. Hello.
Yeah, hello.
Sir, tell the host to change the settings that only you can
Yeah, someone has to
access
change.
that.
Just a second. I'll ask the team. We'll take a break of 2 minutes, then we can change that. Okay. Yeah. And next things like include the testing ensures the chip will functionally work as per the requirement of the application or the customer requirement. Okay. And this will be completed process will be taken in the VLSI design. And the tools used for it are like complete EDA tools, what is called engineering design automation tools. When someone is calling EDA tools, it is called as engineering design automation tools, or the tools main providers are Synopsys and Cadence and Mentor Graphics for this VLSI. Okay, so now understand this is the front end design where the RTL design and functional verification, logic design, logic verification will happen. In the back end, the layout, circuit design, and layout verification, and physical design and physical verification. This all the things will happen. Okay. So just to understand one of the snippet, the behavioral code is like just to understand we will designing some adder. The adder will be looking like a behavioral code like this, the behavioral representation. Then logical representation that will be in the gate level like this. The transistor level, the layout, first the transistor circuit level, they will be seeing the chip like this. That is in a stick diagram for a normal layout. Then again, the layout representation will be done by the analog layout people. Okay, this will be combinedly the putting together by the physical design people and physically they are verified by the physical verification people, and it is tested properly with all the frequency things, how the speed is working, and they will be given to the fabrication people by the end of the design cycle. And that file format is called a GDS file. It starts from the RTL to GDS. Okay, coming to understand how the global market is there. So currently the market is touching at 600 billion. That is like 1 billion is equals to 8,500 crores. I'm just talking about the revenue only, not the market capital. Market capital will be into 50 times. Okay, market capital is into 50 times. That's how the company market is there in the US I'm talking about. So 1 billion is equals to 8,500 crores in Indian rupees. That's how the market is there. And companies like Nvidia, Intel, TSMC, AMD, all these are the major players. Okay, here the Indian machine. So India has started a machine that like spending a 10 billion from last 3 years, and they called a program. It is called Semicon India, and every year it is happening. They are doing something on the to build a semiconductor machine in India. It focuses on the design and manufacturing and packing of the chips to support the domestic semiconductor ecosystem. And we are part of the Skill India development. And we are also part of the Indian semiconductor mission, the ChipXpert. Okay, the ChipXpert, we give the training for the VLSI design courses for RTL design and design verification and physical design and analog layout and DFTs. Okay. So here, India is part of completely like they're spending 10 billion every year, as I said, and the top investors completely they started in India are like Micron, Tata Elxsi, and Foxconn, Vedanta are the top major investors are building the semiconductor ecosystem. And I think recently there is a Vedanta, I mean, sorry, the Adani is also starting their manufacturing unit in Gujarat. And there are a lot of fabrication units are coming, and India will be a global hub for the semiconductor by 2030, I believe. If we are, and 80% of the design teams are in India only, and majority of the companies are focused in India because majority of the engineering sector from the design in India only. So we don't have the manufacturing unit till now, but we have a design teams more. So it's just that we have to focus on the manufacturing unit that India is focusing on currently. Okay. Next, as we wanted to explain about some things about the ChipXpert, what we are actually doing. So under the Skill India program supported by Government of India, we are giving the trainings, and with collaboration with MCA and MSME, this is a national recognition things what we have with the ChipXpert. We provide the hands-on experience for the EDA tool practices from the Cadence and Synopsys tools. At the same time, we have like VPN access for the people who have online and offline with 24 into lab access. And we ensure for all the offline people will get a expert mentorship in the offline, and for online, there is a complete guidance will be given when they're taking on online. And offers complete placement assistance and a complete mock interview preparation for each and every module that will be given for the students. Okay, this is all about the ChipXpert programs. And coming to the mode of trainings, we'll offer a complete online and offline trainings and live interaction sessions also there. I think I can share this PPT presentation for that to get all the features about this. Okay, and we also give a complete recorded session access for the lifetime, and we'll also give tool access till we get a placement also, and doubt clearing sessions for every module that after the each and every session. Every day there will be 2 sessions and 2 practical sessions that are going to happen, and for each and every module there will be exam of grantees and also interview mock sessions that will happen. And having a classroom training in Hyderabad and Bangalore locations we have. We are located in Hyderabad, Madhapur, and in Bengaluru we are located in Bellanduru, opposite to the Microsoft office. And there will be like complete hands-on experience on all the real-time design flows. Each person will get at least 3 major projects and 3 minor projects. That is one of the best things in industry we are providing. Okay. Next thing, this is all about our ChipXpert things, and in the coming now, right? So Ravi will be taking over to give all the hands-on experience from the specifications, designing the real-time chip. So we will be having 2 more days. We are not yet finished. Okay. We have 1 more hour to get the complete from the real design tool things, how the industry is currently working on. Today we will cover a processor called Leon chip processor, which is currently used in the market. And for people who actually we have giving a certification for this workshop who attendedly, we will at the end of the sessions we will give a 1 Google form. They has to fill this to get a certificate for 2 days. So they has to fill for 2 days. They have attended a 2 days workshop. So we'll give a complete understanding of this. So we'll provide the recording session also, and that will be shared in the same mail that you got for the invitation. Okay, we'll complete get all the mail threads regarding that also. Okay, and before starting the things, so just I will take all the doubt sessions at the end of this class, and please please be patient, and please don't interrupt the trainer, I mean the instructor things, whatever they are saying currently. Okay. I'll try to change the settings now because some people might know that what actually happening. Yeah. So thanks for that. And Ravi, you can take the control now. Okay.
So hi everyone. So now we'll see how to design a chip. So what was the different stages we have in front end to design a chip. So
Ravi, you can share the screen if you're not sharing.
Yeah. So are you able to see my screen?
Yes.
Yes, sir.
Yeah. So before going to the Leon processor, we should know what was the things there, what was the stages we have in front end. So before going to that, we'll learn what is meant by RTL. So first we need to know what is RTL. So RTL is nothing but register transfer level. So where we are going to, so it is an idea to describe how the data is getting flow inside a registers. So you know what is mean by register, right? So register is a fundamental building block to store data. So where it is going to store some data. So RTL is going to describe how the data is going to be stored or going to be transferred between one register to another register. So the RTL is going to explain how the data is going to be transferred. That means it is going to describe the behavior of that circuit. So after describing the behavior, we need to design the circuit, right? So we are going to design the circuit in HDL languages. So HDL is nothing but hardware description language. So in these HDL languages, we'll describe the behavior of that circuit. That means we are going to write the code in a textual format. Okay. So what was the different types of HDL languages we have? So the HDL languages, what we have is Verilog, so VHDL and System Verilog. Only so these three languages will provide us to write the data or to try to design the circuits. So after designing the circuits, what we are going to do is we are going to verify the circuits. These are the things what we have in front end. Okay. So Verilog, why we are going to use only hardware description languages to design the circuits? Why we can't use software languages like Python or like Python or Java? Why we can't go for that? Because so when we are writing the when we are describing the code in HDL languages, hardware description languages, so it will make us too easy to simulate or synthesis. Simulation is nothing but verification of your design with passing some stimulus or synthesis is nothing but conversion of your design from textual format to gate level netlist. So these languages are providing us easy to do that. So that's why we are going to do that. Use these Verilog or HDL languages to design our circuit. So and moreover, these languages are providing us the flexibility to design the code in different types of abstractions. Like so when you know the behavior of the circuit, so you can use behavioral modeling. So we have different types of abstractions, abstraction levels. Like behavioral modeling. So, and gate level modeling. And the third one is data flow modeling. And switch level modeling. So these Verilog languages or HDL languages or VHDL language, what it is going to do is it is allow us to write the designs or writing or code in this format. Like so when you know the behavior of that circuit, it allows us to write the circuit or to design the circuits in behavioral modeling. That means by describing the behavior of that circuit, we can write the code here. We can describe by describing the circuit, we can design the circuit. By describing the behavior of it, we are going to design that. And next one is gate level modeling. So when we are going to use this, when we know the circuit diagram. So when you know the circuit diagram of it, you can design the circuit using gate level modeling. And data flow modeling means when you know the equation. So if you see for the full adder, so what was the equation for it? So if you see the full adder, what was the full adder is going to do? So it is going to take 3 bits and it is going to give input and output. So it is going to add those 3 bits and it is going to generate sum and carry, right? So if you see this full adder, it contains 3 inputs A, B, C and 2 outputs, sum and carry. So it is going to add these 3 inputs and it is going to generate the output sum and carry. This is the one, right? What was the equations for this sum and carry? So if you see the equations for sum, so equation what we have is A XOR B XOR C for sum, and for carry it is AB plus BC plus CA. So this is a equation. This was the equation for sum and carry. So when you know these equations, so you can use data flow modeling style to design the circuit, or else when you know the transistor level circuit diagram, like with the transistors like PMOS transistors and NMOS transistors, when you know the circuit diagram of it, you can use switch level. So you can use this switch level modeling style to design the circuits. So and only this Verilog or VHDL or system Verilog is providing us to design these circuits in these levels, in these types of modeling styles. That's why we are going to use Verilog language or VHDL language to design the circuits. And coming to Verilog language, it was used by American based companies and VHDL is used by European based companies. Okay. So if you see this, the next one what we have is, switch level modeling style. So when we are going to use this, when we know the structural transistor level diagram of any logical circuit, we are going to use this switch level modeling style. And the next one is about what was the different steps we have, different stages we have in this front end. So if you see for when you want to design a chip, so what was the first stage? So there are 4 stages we have to design a chip. There are 4 stages we have in front end. The first stage is specifications. So specifications is nothing but where we are going to specify the functionalities or what are the requirements, what was a nanometer, what kind of board we want. So whether you want a FPGA board or ASIC board. So all the functionality, all the specifications, we are going to write it in a specification. It is the first stage of our VLSI front end first stage. And the next one is about architecture. So after giving all your specifications, what we are going to do is we are going to design the architecture here. Okay. Architecture is nothing but we are going to design a chip, like what are the blocks we need. If suppose this is our chip, if this is my board, if this is my board, so I want to write my architecture like, so here I need a processor, so here I need a USB port, so here I need MAC Ethernet cable, and here I need UART. Like this, we are going to design the architecture here. So we are going to design the architecture diagram in the second stage. And the third stage, what we have is we are going to design the code. So after designing the architecture, what we are going to do is we are going to write the code. We are going to design the code in Verilog language, or mostly we follow or we use Verilog language to design the circuits. So why we are going to use Verilog language is most of the industries are going to use this, and it is easy to synthesizable. So this Verilog language is easy to learn and easy to synthesize your design. Like it is providing that flexibility. So each and every tool what we have for synthesis, most of the tools what we use, what it is going to be supported is only this Verilog language is going to be supported by the tools. That's why we follow Verilog to design the codes, Verilog language to design the codes. So if you see the basic structure of Verilog code, so if you want to see, suppose I want to design the code for the full adder only using data flow modeling. So we'll see how to design it using data flow modeling first. So we use this data flow modeling style when you know the equation. So before that, I told you when we use this modeling style, when you know the equation of that circuit, right? So how we are going to write how we are going to design the circuit, basic structural circuit is, first we'll start with module. So it is a keyword and end module. So this is a basic structure to start any of your RTL code. Module and end module is a basic one. We have different kinds of modules and end modules. So to identify the block, what we are going to do is we are going to name a module here. So here I can name, here I am going to mention the name of my module. I can mention whatever the name I want, I can mention here. And here I'm going to write the ports. So ports are nothing but inputs and outputs of your circuit. Suppose let's think I had designing a code for full adder. So if you see this full adder, it will have 3 inputs like A, B, C, and 2 outputs, that is sum and carry. So these are the input ports and output ports of the circuits, right? So here, after mentioning your module name, you are going to write your ports here. So my ports are A, B, C, sum and carry. So here I write my signals, and after that I need to intimate to my module like what was the input ports and what was the output ports of my circuit. So here what was the input ports here? So here input ports are going to be represented with input. So input A, B, C. So these are the input ports of it, and output ports are like output, sum, carry. So here like this, we are going to mention the input ports and output ports. And after that, after declaring the ports and port list, what we are going to do is we are going to write our equation. So what was the equation we got? So we are by using the assign keyword, we are going to write that. So that means assign keyword is a continuous assignment where it is going to continuously drive the data to a wire, So where it is going to continuously drive the data to your output wire. So here it is an output, we are calling it as a wire. So wires won't store any data. So we have different kind of data types in this Verilog. So we have to mainly, it is categorized into two data types, two different data types. So one is reg and one more is wire. Reg is nothing but register, wire is nothing but net. So what register is going to do? So previously we have studied about registers, right? So register is going to store the data, right? So register is going to be store the data, and wire is not, it won't store any data. It's just a physical connection between two blocks. So it is just a physical connection. So here I didn't mention anything. Here I didn't mention anything. So here I want to declare the data type. Data type is nothing but your value that you are given to your input variables. Okay, so here I'm going to declare with wire. So wire is nothing but physical connection. So here we use continuous assignment to drive the data to your outputs. So assign sum equals to A XOR B XOR C. So like this, we are going to write the equation for sum, and for carry, assign carry equals to A and B, or B and C, or C and A. So like this, we are going to design a module. So how it is like this, we are going to design the circuit for a full adder. So
Yes,
this
sir.
is how you, yes.
Sir, I have some
Yes.
network problem. Can go back only for 2 minutes.
Just I need to go back for 2 minutes.
Yes, sir. Because a network problem, I missed it from assigned.
Yes.
Sorry for the interruption, sir.
Yeah, fine.
वो कह रहा मेरा नेट चला गया था पीछे से पढ़ाओ 2 मिनट.
So here, after finishing, after declaring a code list, what you are going to do? So you are going to write your logic. So after writing your basic structure, this is a basic structure of designing your code. So module name, and port list. And after mentioning what are the input ports of the circuit and what was the output ports of the circuit. This is a basic structure. So inside this structure, you need to implement the logic here. You need to design the logic in form of textual formats. So here I can do, here I'm doing using gate level modeling style, right? So when we are using, or when we are designing the code in gate level modeling style, what we are going to do is we are going to write in a continuous assignment. So continuous assignmenting, nothing but we are continuously, so we are going to drive the data to our outputs. That means we are going to assign your data to a wire data type here. So for that, for declaration of that continuous assignment, we are going to use assign keyword. So assign, and here we are going to write our logic. So what was the logic for sum? Previously we have written, right? A XOR B XOR C. And for the carry, so assign A and B, or B and C, or C and A. So like this, we are going to design the code. So here in Dataflow modeling, we are going to use continuous assignments to design the code. So while coming to the next modeling style, so the next modeling style, what we have is behavioral modeling style, right? So in this behavioral modeling style, so what we are going to do? So we are going to design the code by describing the behavior. So previously we have designed the code in equations, by knowing the equations. So here I'm going to describe the code by describing the behavior. So what was the behavior of that circuit? So the behavior of it is for whenever the change in my output. So if this is my if this is my full adder, so where it is having ABC and sum and carry. So the behavior of it is what? Whenever the change happen in my inputs, so my output should be changed. My outputs will be changed here. That was a behavior of my full adder. And there is we are going to do addition operation between A and A, B, C. So that is the word. So how I am going to design here? The same, the basic structure is common. So the basic structure, module and module name and port list, and what are the input ports and what are the ports. Up to here, it is common here. So for everything, it is common up to there. So later, how we are going to design the logic is here. So this model is going to say how we are going to design the logic. So I want to design it using behavior modeling. So how I'm going to do is module. So same ladder name, whatever the name I want, I can keep. So I'm going to declare my ports ABC and sum and carry. So inputs as like A, B, C, and outputs. I'm going to use register data type to my outputs here. So register is going to store the data. So whenever the change happen in my inputs, it should be changed. The output should be changed here. So if there is no data, if there is no input change, what should happen? It should store. It should be constant value. So for that, what I'm going to do is I'm going to use procedural blocks. So if I use always block, we are calling as a procedural blocks. So when we use assign block, assign statement, we are going to call it as a data flow continuous assignment statements. So always at the rate. So I'm going to design a block with this always. In this always, I'm going to design a block. So the block should be triggered. That means whatever the content I'm writing inside this block should be checked whenever the change happen in my inputs. Okay. Always at the rate beginning. So sum equals to, I'm going to write my equation A, B, C, A XOR B XOR C, and carry equals to A and B, or B and C, or C and A. End. So end module. So like this, if we design the code, then we are calling as a behavioral modeling. So here we are going to describing the behavior and we are writing our code. So this is a one way of writing your design. And the next way what we have is gate level modeling style. So what was the gate level circuit here? Gate levels, how we are going to design the circuit for the full adder. So if you see the equation for sum, it is A XOR B XOR C, right? So I have three inputs A, B, C. So where the equation of sum is AB with XOR gate, AB with XOR gate, and C A XOR B XOR C. So this is the equation for sum. So this is a circuit diagram for sum, and we are coming to carry. The equation of it is AB AND gate, BC AND gate, CA with an AND gate, and these two are connected to OR gate. The output of this is connected to OR gate. So this is for carry, right? So this is the circuit diagram of your full adder. So in gate level modeling style, you are going to describe in gates. By calling the gates, you're going to do that. So in Verilog, we have a term called predefined primitives. That means we have some logic already which is predefined in our language. So if we want to use that, so we can call it with that name. So as like that, so we have some predefined primitives, like you know how, hello, yeah. So in this Verilog, we have some predefined primitives like gates. So AND gate, OR gate, NOT gate, XOR gate, XNOR gate, or NAND gate, or NOR gate. So these are the predefined primitives. So their operation is already predefined in our design, in our language. So when you want to use this gate directly, if you call this predefined primitive AND, so can you please mute yourself? So when you want to use these gates, so you directly call that gate. You can directly call, if you want the behavior of AND gate, you can directly call with an AND. Directly that behavior of that gate will come. And if you want to change the inputs, so we have an order to change it. So we'll see how to write that, how to write this ladder using gate level modeling style. So suppose I want to design the same full adder only using gate level modeling. So I'll write them. My basic structure is common, module and module name, inputs and output ports, and everything I'm going to write the same. But here what I'm going to do is just I'm going to change my inputs. So if you see, first gate of my full adder is XOR gate, right? First gate of it is XOR gate. So I'll call XOR. With that, I'm going to write the input ports and output ports of that. So first I need to declare the output port. So if you see this diagram, so this is my first gate. So my input of it is A and B, and output I'm taking as a wire W1. So the output of is W1. This is a wire. Just I'm going to connect my output to my input, right? Next one input, XOR gate input. Just I'm going to take one wire and I'm going to connect this here. So here my output of it is W1 and inputs of it is A and B. So W1 comma A comma B. So like this I'm going to design the XOR gate. So if I write like this, what will happen? Directly the XOR gate functionality will work here. And next gate, what we have is the next XOR gate. So for the next XOR gate, what was the outputs? So output of it is sum and input of it is C and W1. So in output of it is sum, W1 comma C are the inputs of it. So this is how we are going to design sum. So if you go for the carry, so for carry, what was the first gate we have? AND gate. So for an AND gate, what was the outputs? So this is W2, W3, W3. So here we are going to take few wires. Here we are going to take few wires to connect the output to the next one. Okay. So for the AND gate, first input is W1. So, sorry, first AND gate, for first AND gate, the output of it is W2 and inputs are A comma B. So this is for the first one. And for the second AND gate, W3 is my input, B comma C are my outputs of it. For the next one, W4 as my output, C comma A as my inputs. And next one is OR gate. So OR gate, W2 comma W3 comma W. So first OR gate, for OR gate, what was the inputs here? What we have? So W5 as my output, W3 and W4 as my inputs. And next OR gate. Carry W2 comma W5. So like this, we are going to design our codes. So by calling the predefined primitives, which we're calling as gates, so we are going to directly call to design our circuit. So this flexibility is providing by the Verilog. Only Verilog and VHDL is providing this flexibility. So that's why we are going to use this language, HDL languages, to design the code. Okay. And the next one, what we have is okay, so we have finished the third stage, right? The fourth stage, what we have is RTL verification. So the design code we need to verify, right? So when we are designing a code, so we need to know whether it is working correctly or not. So for that, what we are going to do, we need to verify that. So verification is nothing but generating some stimulus and passing it to your design. Stimulus is nothing but your inputs. Suppose if this is your circuit, you want to check it. You want to check it whether it is working correctly or not. So how we are going to check it? So if you pass some inputs, to your design, so it is going to give the respective outputs, right? So that is what checking is nothing but. So here for this design, we are going to pass some inputs like 101 or 011. So like this, we are going to generate some inputs and we are going to pass it to our design, and it is going to give the respective outputs. So that is what we are going to do in verification. So in verification, while coming to the RTL verification, so we are going to do it in system Verilog and UVM, and the methodology what we are going to use is UVM, universal verification methodology. So we can also verify our design in Verilog. So rather than Verilog, mostly we prefer system Verilog. So why we prefer system Verilog more than Verilog? That also I'll say. So usually in past, what we are going to do is we are going to design our circuits in Verilog language. In the same Verilog language itself, we are going to verify that. But later the days are going on. What happened here it is, so the complexity of the design is getting increased, right? So previously we have when a chip is getting started, so there is we have only 120 transistors in my chip. Usually we have the first chip what we have designed with 120 transistors. So at that time the verification of it is easy. The verification of it is easy, but while the days are going on, so the circuit designing is very much complex, and verification also it become very complex here. So what we are going to do is we need an advanced languages and advanced tools to verify our design. So we are going for system Verilog. So what system Verilog providing rather than Verilog is, it is providing us a modularity. So usually in Verilog, how we are going to test our designs. So if you see the basic architecture diagram of Verilog design and test bench. So if this is your design, if this is my DUT. So what we are going to do is we are going to add one more block above this. So this is we are calling as a test bench. So what test bench is going to do is in this test bench. So this is design is one block and test bench is another block. Okay. So in test bench, what we are going to do is we are going to generate some inputs. We are going to generate some inputs and that inputs are passed to your design. That inputs are going to be passed to our design and we are going to verify. So that if I pass some inputs to our design, it is going to give some outputs, right? So the outputs will be collected at my test bench and I'm going to check it whether it is working correctly or not. This is usually how a Verilog test bench is there. So while coming to the system Verilog test benches, the complexity of design is getting increased. So they had modified their test benches also. So while coming to the system Verilog, so we won't discuss about the design part here. So mostly we are going to focus on to verify our design. So to verify our design, that means mostly we are going to focus on our test benches. So in test benches, what we are going to do is we are going to design different blocks in our test benches. Like so, one to generate the stimulus and one to drive the stimulus to our design. So usually all the things are carried out by a single block itself. In Verilog, all the things are carrying are for driving your design or driving your stimulus from design to test bench to design. Everything will be carried in a single block itself. Within a single block itself, everything is done here. But here, in coming to the system Verilog, it is not like that. So we have a separate block will be there to design to generate the stimulus. Okay, that we are calling as a generator. So they will have a separate block to drive the data from design to from the test bench to our design. So that we are calling as a driver, and we have a separate block to verify the outputs. For verifying the outputs, we have a separate block. So like that, so is system Verilog test bench is providing the modularity. Modularity is nothing but designing of your test bench into several parts. So that is providing by the system Verilog. So we are going to do that using OOPS concept. So Java, you know about Java, right? So in Java, we have an OOPS concept, object-oriented programming language. So in OOPS concept, we are going to, in that OOPS concept is used in this system Verilog, and it brings a modularity to design the test benches. And also in system Verilog, we have several advantages like constraints, like usually we have usually every time assigning of inputs to my design linearly, like A equals to 1, B equals to 1 and C equals to 1. So it is very highly impossible to assign linearly, like assigning the values directly. It is very very complex to send the data. So here what we are going to do is we are going to randomize the data. So that means we are going to use rand keyword, randc keyword. So like that, to randomize the data, we have a randomization concept. It providing us the randomization concept to randomize the data or send it the data from the design from the test bench to design, and to control that randomization. So when we use this randomization $random keyword or anything, so we don't have any control over that. So usually we don't have any control. So if I keep something $random, so it is going to generate some random value. So if you want to make control of that, so system Verilog is providing that. So it is going to provide constraints like I need only the value should be generated from particular range. So that things are getting provided in the system Verilog. And next advantage is what we have in system Verilog is it is going to give the coverage report, right? How many values has been generated, how much percentage of what was the percentage of my code, how much code it has been covered. So everything, it is going to improve the quality of your design, quality of your verification. We have a coverage concept. So how many values it has been generated, and sessions, we have few sessions, whether it is working correctly or not. So these kinds of advantages we have. So this is few. So we have several advantages in system Verilog. And we are going to use the system Verilog test benches to verify this. And the next advantage is what we have, and next concept what we have is UVM. So after finishing design, we are going to wait for the verification in system Verilog, and UVM, we have a UVM methodology, and for to verify that, we are following the UVM methodology, universal verification methodology. So in this universal verification methodology, why we are going to follow this is, suppose I had written a code. Okay, so in mid of, so we have doing one project, and so we are going to verify a specified block. Okay, so what we are going to do is, so I got something issue and I had left from the team. So in mid of my project stage, I had left the team. So each and every person will have their own logics, and they're going to design, or they're going to verify our blocks in their own way. So okay, so whatever the code I had written, you can't able to see, and whatever the code you have written, I can't able to understand that. Okay, so to make it easy, what we are going to do, we are going to follow the same structure. So the logic may be different, but writing of code, you should be the same. It should be the same order. That means we can easily understand our code. To make easily understand our code, we are following this UVM methodology, and that was the final final stage what we have in verification. So in UVM, we have set of libraries. So by using that libraries, we are going to extend that libraries, and we are going to design our verification test benches. Okay. So this was the different kind of stages what we have in this VLSI front-end flow. The first stage what we have is specifications. Next one is architecture, and next one is RTL design, where we are going to design the code in HDL languages like Verilog, System Verilog, and UVM. Verilog, System Verilog, and VHDL. And the next stage what we have is RTL verification. In RTL verification, we are going to verify our designs using System Verilog and UV methodologies. These are the where we are going to focus on front end. So when we are choosing the front end as a DV engineer, so mostly we are focusing on these 4 things. Okay. So now we'll see. So this is a basic introduction to VLSI front end. And next thing what we are going to see is Leon 3 processor. So the main intention is how we are going to design a chip, right? So how a chip is getting made. So we'll see in a real-time design what we have done. So that is Leon 3 processor. So Leon 3 is a 32-bit CPU, 32-bit CPU microprocessor. So it was designed by Sun Microsystem company with the architecture, or with the design principle of Spark V8 instruction set architecture. So by this Spark V8 instruction set architecture is nothing but a design principle. So it is going to say how to.
किसी ने म्यूट कर दिया इसको.
Okay, so here what we are going to do is we are going to design this Leon 3 processor. So it is a 32-bit CPU microprocessor. But this was the to design this processor, we have followed the Spark V8 instruction set architecture. It's like a design principle. So while coming to this processor, so if we want to design, we have designed this Leon 3 processor to integrate in SoC. So what this Leon 3 processor, well, coming to the Leon 3 processor family, so it has several versions like Leon 1, 2, 3, and 4. So Leon 1 and 2 processor was designed by European Space Agency. So that was a research center where they had designed this Leon 3 process, Leon 1 and 2 versions. And while coming to Leon 3, so it was designed by Aeroflex company. So this main intention of this chip was to integrate to integrate a processor inside an SoC and to access the external peripherals easily. And it is an open source. And if we see the specification, so while coming to the Leon 1 and 2 and Leon 3 processor, so they had extra features like HB. So they had used HB interfaces, and they had given plug and play option for this. And next one, while coming to that, we'll see how to design this processor. So first, when you want to design a chip, the first part was the first stage. The first stage of it is specifications, right? So specifications, when you came for the specifications, these are the specifications of Leon 3 processor, where we need to design the chip with Spark V8 instructions architecture, and it has advanced 7-stage pipeline, like so to execute so processor is going to be work. How it is going to be work? It is going to work by executing the instructions, right? So it should have should execute the instructions in 7 stages. So that was the specification they are asking to design, and they should have hardware multiple divide and MAC units. And the chip what we are designing, it should have high performance, and it should have separate instruction and data cache memories, and along with that it should have HB interfaces. So if you see, or if you read these specifications, so these are the specifications what they are asking to design. And well, coming to this Leon 3 processor, it can be designed or it can be implemented in FPGA boards and ASIC boards also. So in FPGA boards, how we are going to do is, so we are going to take a software and we are going to dump it in FPGA boards, or else if you want, we can make it in an ASIC board. We can also design it in an ASIC board also. And we'll come into the applications of these. So we are going to use this in spacecrafts or military appliances or embedded systems. Mostly we are going to use this processor in these applications. So the next thing, after specifications, after finishing the specifications, what was the next thing is architecture, right? So we are going to design the architecture. So this is my Leon 3 processor, where it is going to be connected to AHP. Where it is going to be AHP bus. So we have several blocks in that. So we have memory controller, AHP to APB bridges, DRAM, UART, Ethernet MAC layer, or JTAG debug layer. So we have several blocks where it is connected to my processor. Then what will happen here is HP is acting as like a bus, and Leon 3 is acting like a master, and all the peripherals what we have here, right? Memory controller or UART, on chip or Ethernet cable. So each and everything are acting as like a peripheral device. That means here it is acting like a saves. So if you want to make an interconnection over this, what we are going to do is we are going to use AHB bus. So we are going to implement the AHB master block in my Leon 3 processor, and AHB interface in my the peripherals. So AHB interface like a slave block in each and every block here. So we'll see how to design these blocks. So how to write a code for these blocks, we'll see now. So if you want to design a clock, so the next one what we have is, so internal circuit diagram of each and every block. So this was the circuit diagram for Leon 3 processor. So internally what we have. So this is a normal architecture. So if you go deep into that, so this is the first internal architecture what we have. And this is for the memory interface, memory controller. And next one is, this is for UART. This is for UART. And this is for JTAG, and this is for Ethernet MAC layer. So this was the internal structures. So we'll see how to design that. So when you want to design the circuit, when you want to design the when you want to design this code in form of RTL language, in form of Verilog language, so we need to know the behavior of it, right? So we'll see how to design it. So we'll see a small block how to design this. So I will take an external, not an external block, any peripheral device. Let's think I'm going to design it here for FIFO. So first in, first out. So what was the behavior of this? So this was my circuit diagram where I'm going to implement for FIFO. So FIFO have some memory. So first we should know where we are going to use this FIFO. So we are going to use this FIFO to transfer the data in between two blocks. So if this is my block A and this is my block B. So I want to transfer the data in between block A to block B. But here what was the thing here it is. So block 1 is working with different frequency and block 2 is working with another frequency. So here my frequency is not matching. So what will happen? So if I have a high frequency for the block A and low frequency for the block B, let's have the frequency what I have is 100 megahertz for the block A and the block B is triggering at 50 megahertz. Block B is triggering at 50 megahertz. Then what will happen if I'm trying to transfer the data in between block A to block B? So here my frequency is not matching. So there will be some data loss in between. While transferring the data from block A to block B, there will be a chance like data missing. So to prevent that, we are going to use FIFO. We are going to use FIFO. So FIFO, what it is going to do is whatever the data we are sending into this, we won't send the data from block A to block B directly. What we are going to do is we are going to send the data from block A to FIFO. FIFO, what it is going to do is FIFO is going to store the data. So it will have different pointers, read pointers and write pointers. So FIFO is nothing but first in, first out. That means what we have sent first, so that is going to be received the first. Okay. So the data what we are sending from block A, we are going to inside a memory inside a FIFO, and block B is going to read the data what we have sent it first. So while inserting FIFO inside between these two blocks, what will happen? So the data loss won't be happen here. So this was the block what I want to implement now. Okay. So if you see this block diagram of FIFO, so inside a FIFO I have memory. So have a memory and it will have write pointers and read pointers. So what write pointer is going to do? So write pointer is used to write the data inside your memory and read pointer is used to read the data from the memory. So these are the internal signals what we have. And while coming to the external signals, so it is work on clock and it will have a reset signal and it will have data input to write the data and it will have write and read enable signal to write the data or to read the data. So these signal will decide whether to write the data or to read the data. And Dout signal, which the data what we are sending inside a memory to read it out, this was a signal which is helpful to us. And we have two flags. So one is full and one more is empty. So these are the two flags. So what these two flags is going to do? So it is going to describe whether the memory is full or empty. So when it is getting full, when your memory locations what we have here, right? So if it is filled with some data, if all the memory locations are filled with data, so at that time my full will become high. Okay. So if my memory is empty, that means if I don't have any data inside my memory, it will be high. So this was the two flags. So where it going to say whether the memory is empty or full. So when it is empty, it will become high. When it is full, it is the full signal will become high. So this was the behavior. So the behavior of FIFO is what we have inserted first, it should come first. Okay. So this was the behavior. What we are going to do is now we'll design the code for this. So in the tool what we are currently using, so we'll write the code. So we'll write the code for this block. And we'll verify this whether it is working correctly or not. Okay. So here I'm going to create, just wait a minute. So here what I'm doing is I'm going to create one folder. So I'm naming it as a workshop. So this is the folder. So here I'm going to create two files. So or two txt files. So one file is to design and one file is to test it. So now we'll go into the tool. So I need to go. So if you see here, so this is the tool what we are currently using, QuestaSim. So which was designed by Mentor Graphics. Okay, so we are going to we'll see how to design this tool first. So first I'll check where was my current directory. So see this, you can see here I had type PWD, present working directory. So where I am currently. So it is showing some in D volume, in some workshop, some in something folder it is showing. So I want to go to my path where I had created the two files. So now I'm there in my path. So if I type ls, so this is of two files what I had created. So if you see this extension of it, Verilog, so dut.v and tb.v. So .v is going to represent it is a Verilog file. So when you have .sv, it is going to represent system Verilog file. So dot extensions is going to represent what kind of file here it is. So I want to design the code in Verilog languages, right? So here I'm going to write it in dut.v. So now here in this, what I want to do is I want to design a FIFO. So for that, I need to open my design block. So edit space dut.v. So this was a command to open your design file. So if you see here, this was your file path. So this was a file. So here I want to design the code. So if you want to design the code using Verilog language, so we need to start with module and end with in module. So internally, after that, what I need to do? So first one is I need to write a module, and after that I need to write the module name. So I am writing for FIFO. So I had written FIFO, and after that I need to mention my ports. So what are my ports here? Clock, reset, D in, write and read enable signal, D out, full, and empty. So these are my signals what we have. So these are the signals what I have here. And here I need to declare what are the input ports of it. So my input ports of my circuit is clock, reset, D in, and write and read enable signal. These are the inputs. And what are the outputs we have? Output, full, empty, output, range, D out. So these are the input ports and output ports of the circuit. After that, what I need to do? So by describing the behavior, I need to design the circuit, right? So for what was the behavior of the circuit? So if you see the circuit, what was the behavior I told? So whatever the inputs had sent it into my memory, so it should read first, and what I had what was the first data we have, it should read first. Whatever the first input I had sent it, so that input I need to read first. That was the behavior. So before going into that, what I need to do is I need to create the internal signals. So this was the outermost signals. So these are the full or empty or D out, reset, D in, write enable, read enable signal are the internal external signals. So I have few internal signals. So what are the internal signals what I have? So I have a memory block and write pointer and read pointer. So the signals what I have. So I'm going to write my internal signals. So first signal what I want to write is memory. So let's think my width of my memory is 3-bit and depth of is 16-bit. So how I'm going to represent that? So if this is my memory, so this is my memory. So my memory is having 16 locations like this. So each row is going to be represent the locations here. So like this, I have 0 to 15, totally 16 locations inside my memory, and each memory can store 4 bits. So 0, 1, 2, 3. So this is the one. So how I'm going to represent the memory here? So memory is going to store the data. That means it should, if you want to store the data, we need to use reg data type. So how I'm going to write is reg of 3 down to 0, here I'm going to write the memory name mem and so number of locations. So 15 down to 0. So totally I need 16 locations, right? So this is how I'm going to represent my memory. So where I have 16 locations inside each location. So it have 4 bits to represent. Okay. So reach 3 down to 0. Mem 15 down to 0. So like this, we are going to write the memory and declare the memory. And next one is what? So internally, I have few signals. So my signals are reach, write pointer, and read pointer. So these are my 2 signals where it is going to increase, where it is going to point out the locations. So if you want to point out the locations, so we have 16 locations here. So the signal what I am going to represent here, it should generate the values up to 16. Okay, so more than 16 here. So if I write like this, reach, write pointer and read pointer, so it can just generate the values 0 and 1. So it is going to generate the signals 0 and 1. So here I need to declare the width, right? So if I want to represent my value up to 15, at least it needs 4 bits to represent that. So here I'm taking 5 bits, 4 down to 0. So to represent my locations in my memory. So next thing is what? So I need to write the behavior, right? So always I want to design the circuit design this FIFO using behavioral modeling. So here what I'm going to do is using a behavioral modeling style, I will design this. So first my circuit should work or my block should trigger at every passage of my clock. So usually our sequential circuits are going to be work with respect to our clock. With respect to our clock, these sequential circuits are getting worked, right? So first what we are going to do is always at the rate passage. So always at the rate passage of clock. First what I need to do is I need to do reset. So usually my circuits are there in unknown state. That means my memory is also there in X state. All the locations what we have here is by default having X. It is going to store X. So here it is going to store X. So here I need to bring my circuit from unknown state to known state. So for that what we will do, I need to do reset. So when my reset equals to 1, so what should happen here is so I need to bring my diodes. What was the diode we have here? So my output what we have here, diode, should be 0 and my memory also storing by default X. So I need to make my memory from unknown state to known state. So for that what we will do is we'll do reset also. We'll assign whatever the memory locations we have. So we'll insert 0 in all the memory locations. So for I equals to 0, so I less than how many locations I have? Totally I have 16 locations, right? So I less than 16, I equals to I plus 1. So what I'm doing is so incrementing each and every location. So I'm inserting 0 inside my each and every location. So like this, I'm going to make or insert 0 in each and every location. So after finishing this, what we'll do? So reset is finished. So if reset is finished, the next process is, so you need to write your behavior. After finishing the reset, you need to write your behavior. So how we are going to, what was the first one? So when you want to write the data. So how you are going to write the data? So with the help of write and read signal, right? So if your write enable signal is 1, so what you are going to do is we are going to write the data memo of inside my memory. inside my right pointer. So inside my right pointer, so I'm going to send D in, and after writing that, I need to increment it. So RT of PTR equals to read right pointer plus 1. So like this, I'm going to increment my pointers here. So the next thing is after writing that, okay. So after writing you need to read it, right? So when your write enable signal equals to 1, you are writing the data. If it is 0, you will read the data here. So when your write enable signal equals to 0, so what you will do? You are going to read the data. So how we are going to read the data means, reading of data means whatever the data we have in my first memory location, it should assign to D out, right? So D out equals to mem of read pointer RD underscore PTR. Okay. And next one is after reading the data inside the pointer, you need to increment your pointer. You need to increment your read pointer. So read PTR equals to RD PTR plus 1. So like this, we are going to write the data or read the data from the memory. So after finishing all my logic, so I didn't write any full and empty condition, right? So when I can write the data, when my write enable signal equals to 1. So if I want to write the data, it should be empty, right? It should be, sorry. If I want to write the data, so my memory should have some space. So when it will allow you to write, when your write enable signal equals to 1, and when it is not full, right? When it is not full, that means when your memory is not full, it is allows to write the data. When your memory is, when you are going to read the data, when your right pointer is 0 and it is not empty. So when it is okay, when it is not empty. So this is the way to design your FIFO, and here you didn't return your full and empty conditions. So you need to write that using continuous assignment. So assign full equals to, when it will be full, so first we'll write for empty. When it will be empty, when I don't have any data, that means my right pointer and read pointers should be there in same address location. When those two are in same address location, I'm going to write the data. So when my right pointer equals to read pointer, I'm going to write the data inside my memory. And next one is, so after finishing the empty condition, I need to represent my full condition also. So when it will be full, when my first address location, so when my right pointer MSB bit is not equals to read pointer MSB bit, and later all the bits are same, then my full condition is getting high. Okay. So how I'm going to write here? So not of right pointer of 4, this is my MSB bit, comma, right pointer of 3 down to 0. If this is equals to read pointer, the condition what we have here, so if this is equals to the read pointer, if this condition is getting satisfied, so it will be your full condition is getting high. Okay, so this is the simple way to design your FIFO. So this is the way to design your FIFO. And next one, what you need to do, so design one, you need to verify that after designing of your code, you need to verify that. So how we are going to verify? You need to pass your some data to your design block, right? So we'll write test bench for that. That means you need to write the test bench here. So we'll write the test bench for that. So first enable that one, edit space tb.v. So you can see here tb.v file. Just allow you to write the data and write module and module name as tb. So end module. So after that, here you need to generate the stimulus in your test bench block. You need to generate the stimulus to your inputs and you need to verify the design whether it is working correctly or not. So here you need to mention the signals as how we have mentioned here. Okay, so here all the signals what we have as an input should be range data type in our test benches. So clock, reset, in, and right pointer. And next one what we have is wires. So whatever the signals we have for output as an output for my design, it will be act as like a wire. Okay, so here previously what I had it is I didn't mention any range for my inputs. That means it is also a single bit. It is a single bit. So I want to give some values. That means I need to give some range to my inputs. So read down to 0 of din. That means my din can generate values from 0 to 15. So okay, I had given the range 3 down to 0, which where it have a capability to store 3 bits. So that means it can generate the values from 0 to 3. Sorry, it can generate values from 0 to 15. As the same way, my D out also. So reach 3 down to 0 of D in. So like this, I'm going to design my declare my signals, and after that, what we are going to do is, so we need to generate a block. We need to generate the stimulus, right? So for generating the stimulus, we need to assign some values to my inputs. So generating of stimulus is assigning some values to my inputs. So first what I'll do is I'll going to assign clock. So I'm going to give some value to my clock. So clock equals to 0. So that means my clock is 0. That means clock should oscillate for every certain time period. So that I'll do with always clock. So but starting for so it should toggle from 0 to 0 1 0 1 0 1 like that, right? So initially if it want to toggle, if it want to start the clock, if you want to start the clock, just here we need to assign a value to that. Just it is a key to generate a clock. Just if you want to start a bike, how we are going to insert a key and we are going to run it, right? So as the same way, the clock equals to 0 here. If we declare here, the next it is going to oscillate from 0 1 0 1 like that. So reset equals to 1. So I want to do reset. That means initially my state is in unknown state. When reset equals to 1, so it will bring from unknown state to known state. So after certain time period, so it is 0. So I'm making it into 0. So that is where it need to be worked. And later what I'm doing is I'm inserting some data to my inputs din, and I'm enabling to write it in. I'm enable my write address. So I want to, if I want to write the data inside my memory, I want to make it my write enable signal equals to high. So here I'm making write enable signal equals to high. So after 100 nanoseconds, I'm leaving empty. Okay, we'll send some other data, 11. And after some other time, I'll send din equals to so. So I had sended 3 data. So did I mention any address locations? I didn't mention any address locations. So first data what I had sent is 10, next 11, next is 12. So these are the three what I had did. So I don't want to read, just I want to write the data inside a memory. So this is how I'm going to design. And next one is I need to generate a clock. Always #5 clock equals to negation of clock. So this is how I'm going to generate a clock. So this is it is going on continuously executing this always block what had written to generate a clock. It is going on continuously executing until your simulation is getting end. So here externally I need to specify to end the simulation. So for that we have a system task, what we call it as a $finish. So $finish you are going to use system task $finish to stop the simulation for certain amount of time. So after starting your code, so if I want to stop my code or if I start execution of my design after 100 nanoseconds, we are going to use $finish to finish it. Okay. So before so can you please mute yourself? Okay. So before finishing of my simulation, before stopping of my design simulation, what I want to do is I want to check. I want to see the values what it has been generated. So for that we are going to write the monitor to see the $monitor. So I want to see reset and DIN input. I want to monitor these values, what it has generated, what was output we are getting for that. I want to check it. For that, we are going to write all the signals to see that. So write and read enable signal and out and full and empty. So full empty, comma, reset, in, write signal, read, full and empty. So hash 100 nanoseconds $finish to stop my execution. Okay. So after writing that, so I need to make a communication block in between my design and my test bench. So here separately I had written my test bench and separately I had written my design, right? So I need to provide the communication. That means I need to do instantiation between my design and my test bench here. So that is we are going to do with through instantiation. So how we are going to write that instantiation is with this DUT name. So DUT, what was the DUT name I had mentioned? FIFO, right? Just what I'll do is just I'll paste it here. So FIFO, first we are going to call my DUT name FIFO, and later we are going to do one instance to that. And next thing what we are going to do is so dot clock of clock. So we are going to write instantiation like this. That means we are going to mapping in name wise. We are going to make communication between my duty and test bench through named mapping. So here the clock what we have outside of my parenthesis is belonging to the DUT to the design, and the clock name what we have mentioned inside the parenthesis is belonging to the test bench. Okay. To the reset dot din of din dot right of right dot so dout of dout dot full of full and dot empty of empty. So this is how we are going to do instantiation between my design and my test bench. So later, after finishing my design and my test bench, what I need to do is I need to run this code, right? So for to execute this block or to execute this code, so firstly we have mainly 3 steps. So one is simulation, sorry, one is compile, next one is simulate, and next one is run. So first compiling is nothing but checking whether whether we have any errors in our design or not. So how we are going to check that? So vlog space. So vlog is a command to compile the code. Vlog space. So what are the files you have? What are the files you want to compile? So dut.v space tb.v. Okay. That's it. So here we are finding one error in our design. So we are going to go there. So here I had declared an integer I, but I didn't declare any data type to that. So integer I. So after saving this, so again go there and do compiling. So compiling is finished. So you don't have any errors in your design. So next one is what? So you need to check it. Checking is nothing but passing of your design, passing of values to your design. So where you have generated your values, you have generated in your test bench, right? So vsim space. So here you need to mention the test bench name. So what was the test bench name I had given? TB, test bench. So TB. So here I'm going to do simulate. So here we are finding TB.24th line. We are going to find some error. So it is full, not done. So again we are going to save this. Simulate. So simulation is finished. And next one is run all. So we are going to run this. Just wait a minute. So simulate. So we can see few things here. So we have sent some data. We didn't get any output here. So why didn't get any output? Since I told to write the data. So I told to only to write the data. That means, so we need to check our memory. So if you see here, inside my memory. So what was the memory name I had given? Mem, right? So see this. You can see a testbench.a1.mem. That means in my design file, I have a memory block with a name mem. So where it is having how many locations? So where it is having 16 locations. So you can find those 16 locations here, 0 to 15. These are my 16 locations. And in first location, I had sent it 0. Sorry, in first location, first I had randomized 10 value. So I had passed input to 10. So it is stored in my first address location. And next, after some time, I had sent it 11. So it is stored in my first memory location. And after some time, I had sent it 12. So it is stored in 13th address, second address location. So what about the remaining things? Why we got this? So here after storing also, I'm waiting for 6 more cycles to I'm running extra 6 more cycles here. So if I don't want to see that, what I'll do here it is just I'll change my right pointer to one tick binary X. So here you can see it clearly. So compile, simulate, run. So if you see here, if you go to the memory list, so in memory list, I have few memories, just to see the content. So what we have here, so in 0th memory location, 0 is stored. So in first memory location, 10, 11 is stored, and second address location, it is storing 0. So why it is storing 0? Because so at the same interval of time, I am changing my right pointer. So here itself, the same time interval, I am changing here. So what I want to do is after some time, I want to change it. So after writing the data, if I want to change, I will get it. So after finishing this, if I want to read, so I will make my write and read enable equals to 0. So what will happen here? So whatever the thing I had written here, so it will be read. So it's compile, simulate, run. So if you see here, what we have sent it to our memory locations. So 10, 11, 12, right? So see these D out. So what we have sent, we are getting the same. So in first address location, we have sent 10, so that it is read. And second address location, we have sent it 11, so that is read. And third address location, we have sent it 12, that also we have read. So this is how we are going to design the Verilog code. Okay. So it's the same way. So with the same behavior, so we are going to define the logics. So it's how we have designed for the FIFO. As the same way, each and every block will have their own behavior. So what we have did here, so by using this Verilog language, by describing the behavior of these blocks, we have designed the code. Okay. So this is all about VLSI front end. So from specifications to till our verification in functional verification, till the functional verification. Okay. Can you please wait for some minute?
Yeah, thank you. People are asking a lot of things in the chat. So just wanted to clarify, you will get a recordings with along with your certificate generation.